Welcome back. All right, the content of this class is coming fast at you. Do you feel the pressure yet? And that's not actually what I mean. What I mean is, can we write equilibrium expressions when we're talking about gases and pressures, or can we just do it when we're talking about concentrations? Because quite honestly, I mean, when's the last time you said, oh, I've got this gas in here and it's got a concentration of 0.35 molar? You don't say that. You say, oh, the pressure of that gas is 550 torr, or whatever it is. And so can we write our equilibrium expressions when we're talking about pressures, or do we have to convert everything to concentrations? Okay, so if we have our favorite generic reaction, AA plus BB goes to CC plus DD, and these are all gases. What can we do? Can we just write a K? And the answer is yes, we could write a K, and we could write the concentration of each one of those, and write concentration of C to the C, concentration of D to the D, divided by those other things. But it turns out if we want to do it in units of pressure, we can. But what we have to do is specify that we're not doing a concentration K, which is K or KEQ, or some people will even use KC, but we're doing a pressure K, and so we use Kp to say this is just an equilibrium constant. It's just going to be products over reactants raised to their powers, but here I'm talking specifically about pressures. And so what's that going to look like? It's going to look like the partial pressure of C raised to little c times the partial pressure of D raised to the little d over the partial pressure of A raised to the little a times the partial pressure of B raised to the little b. And Professor Clemens, you're asking, what was partial pressure again? I understand pressure, but what's a partial pressure? Remember, if you have a gas in a system, right, and you have a second gas in there, let's make it red. Each gas is exerting a pressure on the container when it hits the walls. And partial pressures basically say this, is each gas in here, so the red gas, if you put the red gas in that box all by itself, I'm just going to make up a number, it would be exerting 1 atmosphere of pressure on the box. And the purple gas all by itself would be exerting 2 atmospheres of pressure on the box. When you combine them, you get a total pressure, which is just the sum of the partial pressures. That's Dalton's law of partial pressures, if you remember that. But what we say is that in that box, even though the total pressure is 3 atmospheres, we say the partial pressure of the red circles is 1 atmosphere, and the partial pressure of the purple circles is 2 atmospheres. So the partial pressure is just the pressure it would exert if it was there all by itself, which is pretty much equal to the pressure it exerts when it's around other things. Why? If you remember, a gas is about 99.97% empty space. So you're filling your lungs with mostly nothing, but luckily you can still breathe. Right, we can also calculate it if we wanted to. We could say that the partial pressure of A is the mole fraction of A times the total pressure. What does that say? Hey, if I've got, and I should make my things match here. If I've got that as 1 atm, then I should have 1 less circle there. If I've got a total pressure of 3 atmospheres, I say, well, what fraction of that is A? In this case, let's say we were talking about the purple ones. The fraction is 4 out of 6. That's my mole fraction. 4 purple ones for 6 total times the P total, which was 3 atmospheres, would get me the pressure of my purple ones, which would be 2 atmospheres, because this one was 3 atmospheres. So it just says, hey, the pressure of each thing is related to how much there is times the total pressure. Okay, so there's different ways of calculating reference pressures. Now the question is, can we take this Kp that we now have and relate it to Kc? And, well, let's think about it a little bit. Is there a way to relate pressure and concentration? Professor Clemens, that doesn't talk about concentration anywhere. Well, what's concentration, right? Usual units of molarity, moles per liter. What in here is moles, that's N. What in here is liters, that's volume. So what I can do is I can actually just solve for a relationship between pressure and concentration by saying P is equal to N over V times RT, right? This is concentration. And now I have a relationship between pressure and concentration, at least for an ideal gas, right? It's not perfect, but it's for it's a good pun, right? But it's at least for an ideal gas, and it'll get us a relationship here. I'm not going to do the math for you, but basically, if you take all your pressures and you substitute this equation into your Kp up here, what you'll find is this, that your Kp is equal to your Kc. I could write that as Keq. I could write that as K plane, right, with no subscript, or I could write as Kc. Here I'm going to write Kc just to be very, very clear that I'm talking about the concentration unit. Okay? But K, Keq, and Kc are all identical ways of talking about the concentration-based equilibrium constant. So Kc times RT, hey, that comes from that term, to the delta N. What is delta N? Delta N is just the sum of your product stoichiometric coefficients, little c plus little d, minus the sum of your reactant stoichiometric coefficients, A plus B. So if you had 4 reactants, you'd say A plus B plus F plus G, or whatever they were. So that's what delta N is there. And that's a relationship between Kp and Kc. And we'll need that. We'll use that definitely in several examples. You may even end up using that on a test somewhere. Okay. So let's go ahead and do an example using that relationship. So we're going to calculate K and Kp at 25 degrees Celsius for this reaction based on the following equilibrium pressures, right? We have to have equilibrium values here if we're going to calculate K. Once we have K, we're going to find we don't need equilibriums. We can calculate equilibriums. But in order to calculate K, we need some equilibrium values. And so we've got equilibrium pressures here. So we're going to write Kp in the form of it of NOCl squared over NO. What did I do, right? Just by default, I started writing out my concentration-based one. And I was like, hey, wait, I'm writing out a Kp. Right? I teach this stuff for a living, folks. You're learning it. Guess what you're going to do sometimes? You're going to write down the wrong things. It's okay. It doesn't mean you're a bad person. Right? It just means you made a mistake and you move on. So I was like, oh, I was partially through that problem and I realized I made a mistake. Doesn't mean I don't know this stuff. I know this stuff pretty darn well. But it does mean that I need to go through and fix the mistake that I made. Since I'm talking about pressures, I need to write the partial pressure of NOCl, and I'm going to square that one, divided by the partial pressure of NO squared times the partial pressure of Cl2, and that's to the first. All right, what do I put in here? Well, just like with Kc, turns out we don't want units in our Kp, and so we divide all of these by a reference pressure of 1 atmosphere. You got it. We don't do that explicitly. No one ever writes down 0.3 atmospheres divided by 1 atmosphere, cancel out the unit. They just write down as if it had no units. But you have to remember, very important, that the units here were atmospheres. Right? So anytime you're doing anything with Kp, you have to required units for Kp is atmospheres. So if you're given things in torrs or pascals or anything like that, you got to convert it. Make sure you have atmospheres before you move on. Luckily, we don't have to do that in this case because it was given to us that way. So NOCl, that was given to us first. So we're going to say 1.2 squared divided by NO, 0.050 squared times Cl2, 0.30. Again, no units because they're all divided by a reference concentration. We go ahead and we plug that into our calculator, and you should get somewhere around 1900. So that's our value of Kp. No units because our equilibrium constants have no units. And what we're going to do is we're going to try to go ahead and take that and convert that over to a Kc value. So we're going to use the relationship that Kp equals Kc times RT to the delta N. Let's go ahead and calculate delta N. It's stoichiometric coefficients of all your products minus the stoichiometric coefficient of all your reactants. So I have 2 on my NOCl. That's my only product. So I'm just going to do that. And then 2 plus 1 are my 2 reactants, 2 on the NO and 1 on the Cl2. And so I get that delta N is minus 1. And I get that Kp is Kc times RT to the minus 1, which is the same thing as Kc over RT. That's just what that minus means. I want to solve for Kc, so I'm going to multiply both sides by RT to get that Kc is Kp times RT in this case. Now, R, you have all sorts of values for R, right? You can look up, there's Wikipedia pages about, here's the thousands of different values of R for all these different units. The only ones we ever care about, really, are two of them, 0.08206 liters atmospheres per Kelvin mole and 8.314 joules per Kelvin mole. Everything else we can convert all of our units to conform to our R rather than converting our R to conform to our units. Which one do we want here? Well, we were doing the ideal gas law. The ideal gas law talks about pressures and volumes and things like that. So we're going to use our 0.08205. So we're going to do 1900 here times 0.08206. Now, I'm going to do something I hate doing. I'm not going to put units on this number. It just bothers me to no end, I got to tell you. I'm not going to put units on this number. Why? Because Kp has no units and Kc has no units. If I put units on this number, then I'm going to get units on one of those things, and I don't want that. So I've got to do that, and I'm just going to leave it off of units. If someone who is much smarter than me is watching this video and understands where those units go in this equation, I've tried to find it for years, and I've never been able to find it. I'm probably just not looking in the right place. Please leave a comment and let me know if you know where did the units go in this equation. Is RT actually divided by a reference RT? I don't know. I've never been able to find that. And I said 25 degrees Celsius, we have to use Kelvin here. Remember, whenever we're doing gas laws, you have to use Kelvin. So I take that to 298 Kelvin. I multiply that out, and I get a value of 4.6 times 10 to the fourth, so about 46,000. So here my Kc was much larger than my Kp. That's fine. Sometimes you'll get Kp larger than Kc. It depends a lot on those stoichiometric coefficients and that delta n that you get. Again, no units on my Kc. And now I found Kp and Kc. Your turn. So we've got a reaction here, very complicated looking reaction at 350 degrees Celsius. I'm giving you the value of Kp as 1.83 times 10 to the 23rd. Yes, 1.83 times 10 to the 23rd. Very big number. We'll figure out what that means in a little while. What I want to know is what is the value of Kc? Go ahead and try that out and then check in. What did you come up with? Well, let's work it out. We've got Kp equals Kc times RT to the delta n. Hopefully you figured out your delta n is going to be all of our product coefficients, 4 plus 5 plus 2, minus our reactant coefficients, 2 plus 7.5. Can you have 7.5, Professor Clements? Yes, because that's how your balanced chemical reaction was written. And if you were given a K for that balanced chemical reaction that had a 0.5 in the stoichiometry, you better darn use a 0.5 in the stoichiometry. I'm of the ilk where I'm okay with halves on things like O2, right? Things that are pure like that. I don't mind halves too much. I know some people would multiply this by 2, but it turns out we'd get a different K value. So yes, we can do that. If you calculate all that out, you get a delta n of 1.5. So we are given a Kp. We're going to try to find our Kc. So we're going to plug this in. Kp is equal to Kc times RT to the 1.5. Divide both sides by RT to the 1.5. And we get that Kc is going to be Kp over RT to the 1.5. The things we have to remember is to do our conversion of our Celsius to Kelvin by adding 273. Use our R value of 0.08206. And then make sure to use parentheses here when you're putting that in your calculator so that you take the entire denominator and put it to the 1.5, not just the temperature to the 1.5. If you plug all that in your calculator, what I ended up with is a 5.10 times 10 to the 20th. And if we go up, that is going to be, helps if you do your decimals right. 5.01 times 10 to the 20th. It is B up there. So that's the answer for that one. If you're having trouble with that, you can always email me or we can figure it out together sometimes in office hours. Good? what do we do about solids and liquids? How do solids and liquids come into our K values? Right, so let's look at this reaction. We have a solid calcium carbonate forming solid calcium oxide and CO2 gas. Let's go ahead and write our K expression here. And we're going to say it's the concentration of CaO times the concentration of CO2 over the concentration of CaCO3. Looks something like that. So I'm going to ask you a question here that doesn't look like it's related to this problem, but it is. I've got a bucket of water here, right? Just pure water. What's its concentration? Well, it turns out if you do some calculations using the density of water and things like that, I believe what you get is about 55 molar. Water is about 55 molar. Now, if I have twice as much water, what's the concentration of that water? It's about 55 molar. Why? Because concentration doesn't depend on quantity, right? I have more of it, I have less of it, the concentration is still the same. The total amount of water I have absolutely changes. If I've got salt water and I say the concentration is 0.1 molar, if I double the amount of stuff I have, then I have twice as much salt. But the concentration of salt is still 0.1 molar, right? As long as I didn't dilute it. I just said I've got now twice as much solution, right? So, what do we have? Solids are the same way, right? A solid just sitting there has a certain concentration. It absolutely does. But if I use up half that solid, have I changed the concentration of that solid? The answer is no. I've changed the amount of solid. I have half as much solid as I used to, but the concentration takes into account volume. So I've got half as much solid, which now takes up half as much volume, and the concentration of that solid doesn't change. So this guy actually here is a constant. In fact, this guy here is also a constant because he's also a solid. So now I've got a constant that is equal to some other constant divided by some other constant times the concentration of CO2, right? So I could solve this and say that K times K3 over K2 is equal to CO2. And I probably shouldn't have used capital K's here because they aren't equilibrium constants, they're just constants, but I did. All right, but what's a constant times a constant divided by a constant? Well, that's just a constant. And so what we do is when we write equilibrium constants for reactions that have solids and liquids in them, since the concentration of those solids and liquids don't change as the reaction progresses, we don't put them into our equilibrium expression. We actually kind of just bring them all in to that K value there. And so our equilibrium expression for this is actually just K is equal to the concentration of CO2. So we do not include solid and liquid phases in K expressions. This is true for K, Kp, and all the other Ks that we're going to be doing this semester, no matter what letter we have down there. We do not put solids and liquids into the equilibrium expression. We kind of build those in to the K value itself. All right. So what does K mean? Right? When I have these K values, what does it mean when I say I've got a reaction, methane and oxygen makes CO2 and water, and K is 10 to the 140th? Right? If we write our K expression, the concentration of CO2, concentration of H2O, squared concentration of CH4, and the concentration of O2 squared, right? What does that mean? Well, concentrations can only get so big. I mean, I just told you that pure water, fairly dense molecules all kind of pushed together, has a molarity of about 55. So these numbers are never going to be huge, right? They're going to be maybe big-ish, right? But they're not going to get 10 to the 140th. I mean, you're not going to get a concentration of 10 to the 50th, right? And then you're going to square that and you're going to get to, no, you're not, it's impossible. So if those numbers are never huge, how do I get a number like 10 to the 140th? These numbers have to be absolutely tiny, right? Because if you divide by 10 to the minus 50th, you get a 10 to the positive 50th. So that's what it means. When I have this huge, gigantic K value, It means at equilibrium. Remember, K values are always at equilibrium. These reactants have to be absolutely tiny, 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 tiny. And what does that mean? It means that at equilibrium, I have almost no reactants left. And so when you have these very, very large K values, oftentimes instead of writing these equilibrium arrows, which are technically the correct things to write, you're just going to write a right-hand arrow like that and just say, hey, this stuff reacts till completion. That's what a very, very large K value means, is this reacts to completion. You don't often see CO2 and water forming methane and oxygen. Just not very common. It's theoretically possible, but just not very common. The amount of methane and oxygen left is essentially zero at equilibrium. It's amazing to me that they can even measure that equilibrium constant. What about a tiny, tiny, tiny equilibrium constant like we have for this second one? If we have that second one, we can go ahead and write a K for that one. And we say K is going to be the concentration of NO squared over the concentration of N2 times the concentration of O2. And again, we're never going to have very, 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 very large concentrations. That's just not possible. So those are never going to be huge. How do we get a tiny, tiny number? We must get a tiny, tiny number by having a tiny, tiny number on top. If we have a tiny, tiny number on top and we square that, we're going to get a very tiny K value. So what does that mean? For a very small K value, it means we are not making very many products. So even the value of K can tell us something. If it's a very large value, it tells us we're making essentially all products and we don't have very many reactants left. A very small K value says, hey, we're essentially making no products and we have only reactants left, right? It's fire plus rock. Very heavily weighted towards the fact that rocks are not going to combust for the most part. So we can use that. And what people say in general in terms of language, is that if K is less than 1, the reaction favors the reactants. It's absolutely possible to come up with a circumstance where there's more products than reactants when K is less than 1. However, the language people use, if K is less than 1, we call it favoring reactants. If K is greater than 1, we call the reaction favoring products. And the sticklers among you out there ask, well, what if K is equal to 1? Well, that doesn't happen very often. Your chances are pretty slim. So considering your range is 10 to the 140th down to 10 to the minus 31st, the chances of it being exactly 1, not really worth worrying about. But in that case, it would neither favor reactants nor products. Okay. So that's just language that people use that you should be familiar with. If I say, oh, does this reaction favor reactants or does this reaction favor products? You're really just looking at the value of K. Is it bigger than 1? Is it less than 1? All right, so that's the end of that section. Hope you learned something about how we write different K expressions when we talk about pressures, when we talk about solids and liquids, and a little bit about what that K value means. Big K, lots of products. Little k, mostly reactants. Thanks. Have a good day.